Alright, so let's look at some problems involving phase changes. One we'll solve mathematically, the other we'll just set up an equation, and the third one is a basic conceptual question. Alright, so the first problem is how much energy is needed to completely melt a chunk of ice that is initially below zero. Remember, ice can be as cold as it wants to be. It does not have to be at the freezing point. When setting up these problems, it's very similar to the calorimetry problems, but with phase changes, there's an added complexity to it. So the best way to approach these problems is use the phase change diagram here. What we want to do is we want to pick a point where we're starting. So since we have a solid, we know we're somewhere on the first segment, below the melting point line, but it doesn't matter where we start. So I'm going to put a dot here. And then we read carefully to where you're ending. So in this case, we're just completely melting it and doing nothing more. So we're ending right at that spot there. Anything further up, we now have liquid that's warming up. So that informs us on how to set up the problem. So we're going to have energy. There's going to be heat flow. All right, we're assuming this is due to some warming source. That's going to a change in energy. And now we can use each of those two terms. We have two segments. We have a warming segment as the solid warms up, and then eventually it's going to melt. So as it warms up, we're going to have an MC. Now this is the specific heat of the solid, delta T. And then we're going to add a term for melting. We're not going to partially melt, we're going to completely melt. So it's the whole mass times the latent heat of fusion for that particular substance. If we only melted half of it, then this term would still be 0.10 kilograms, but this term would be 0.05 kilograms. So you got to be careful about that. Alright, so I'll let you put in the numbers. Note that the specific heat of ice, that's not something you would know off the top of your head, is 2090. I'm not going to put the units here, so it's roughly half that of liquid water. Delta T in this particular case is known. We start at -10 and the melting point of water is 0, so that's necessarily going to be a positive 10. We want that term always to be positive degrees Celsius. And then the latent heat of fusion of water is given above, so I'll remind you that's 3.33 times 10 to the 5th joules per kilogram. Alright, and if you put in the numbers, okay, so I'll do it below here, for the MC delta T term, we see that it turns out to be 2090 joules. And the MLF, or the L term, turns out to be 33,300 joules. So I point that out because we see that much of the energy is dominated just in melting it, not warming it up. And that's usually going to be the case. So we just simply add these together, and we get a pretty straightforward 35,400 joules. Okay, again, most of it coming from melting, not warming. All right, next problem. A little bit more complicated. All right, and it says, set up an equation for equilibrium temperature when a small amount of 10-degree ice, negative 10-degree ice, is placed in a bowl of warm water. We're not given the initial temperature of the water, but we know it's somewhere in this part of the graph. So to help set this up, we can basically have heat flowing two ways, flowing into the ice and flowing out of the warm water. All right? Much like we put a warm chunk of metal in our water, we have to set up an equation for both sides of the equation. And the easiest way to help us set up, again, is to use this graph. So we're starting here, again, in the solid on one end, and we're starting here, I'm going to put an X on another end, somewhere in the liquid phase. And then what we want to do is figure out where are we going to meet. Are we going to meet in the solid phase? Are we going to be half solid, half liquid? Or are we going to meet in the liquid phase? Now, based on this, we have a small amount of ice, a large amount of water, so it's fairly safe to assume, but it's not obvious, but we'll make the assumption that the ice is going to completely melt and then maybe start warming up. And then our water is just going to cool down, but it's not going to melt. We can't have both of those. So let's just put a little mark right there. That's where the equilibrium temperature is going to be. Okay, so what this does for us is we have on the left side of the mark our left equations, and then to the right of it is our right equation. So we see on this side there's only one thing happening, cooling down, so there's going to be one term. To the left of this mark there are three things happening, warming up, melting, and then warming up again in the liquid phase. So we need to account for all that. So we're going to start off with the left part. We have the mass of the ice, C of the ice or solid, delta T. Now since we're going from -10 to 0, I'm just going to put in the 10 here, because we're going to have different delta T's based on the phase. Then we have the M, LF. Okay, we know it's all going to melt. And then we're going to have the warming in the liquid phase, that little segment there. So again, we have M, C of the liquid, the water, and then we don't know what delta T is going to be. We want it to be a positive term, so that's going to be the equilibrium temperature minus the initial temperature when it was a liquid, which in this case is 0. Okay, I'll leave it to 0 there, but that certainly reduces to T equilibrium. Okay, so that's the heat flow in. It's going into warming, melting, and then warming again. So the heat flow out is basically M of the small amount, so I'm going to put M2 here, C of the liquid, and then delta T. Okay, we don't know the equilibrium temperature, but let's assume we know the initial temperature minus the equilibrium. Okay, so there's a lot of little details you have to put into working out this type of problem and keeping track of terms. The best way to do that is, like I said, mark where you're beginning on both ends and then where you think you're going to start. We'll talk about what happens if you're somewhere in here where the water starts to freeze and the ice starts to melt. Okay, last question. How does the specific heat of the liquid phase compare to the solid phase or the gas? Let's just focus on comparing liquid to solid. We already know by numbers that the specific heat of water is about 4,000 and it's about 2,000 for this. But how do we see it on a graph? Once again, it has something to do with the slope. Okay, so let me erase that. So we can see the slope of the solid phase is steeper than the liquid phase. So not the length of the line, but rather the slope. So what we know is that slope is inversely proportional to 1 over the specific heat. It's not exactly equal. There's a mass term in there, but that's all we need to know. So the higher the slope, the lower the specific heat. So we know that C solid is less than C of the liquid. Okay, so that concludes 3 simple problems with phase changes.